Welcome to Spring LIB.
Number 40 is a relatively difficult question. We still refer to figure 19 in the chapter, but now we want to be more quantitative. We assume that the two sections has linear density mu1 and mu2. And we consider this point to be the origin, x equals 0. So a sinusoidal wave starts at the left hand of the chord. So initially we have d equals a sine k1 x minus v1 t. Traveling to the right, and then it reaches the knot. It reaches the knot, and then part of it is reflected and part of it is transmitted. The reflected part is AR sine v1 x plus v1t. So it's the reflected wave should still have the same wavelength, same frequency, etc. So everything here, it's still k1 and v1 because it's still the same media, except that the sign changes because it's traveling in a different direction. But the transmitted wave, because it's in a new media, it becomes k2 x minus v2t. It's also a different velocity because it's different media. So, okay, now we say because the frequency is the same, we have omega 1 equals omega 2. What that means is k1 v1 equals k2 v2. We have three parts. Part A asks, the chord is continuous, so a point that is infinitely close to the left must have the same displacement as a point just to the right. So because of that, shows that A equals AT plus AR. So this, when a point is infinitely close to the left, we can, so there must be, it must have the same displacement as a point just to the right of the knot. So the point just to the left of the knot, it has a superposition of both the initial wave and the transmitted wave. So that gives us the amplitude d to the left equals a times sines k1 x minus v1t plus ar times sines times k1 x plus v2t. And because it's very close to the knot, x is almost 0, we can treat x as 0. So now this is v1. So now this becomes a plus ar times sine minus k v1t plus sine k1 v1t. Sorry, so maybe the best way to write it is a times, I'll write them separately actually. So this is a times sine negative k1 v1t, which equals negative a sine k1 v1t, because sine of negative something is negative of sine something, plus ar times sine of k1 v1t. That is d to the left. To the right, we have a t equals sine of negative k2 v2t equals negative at over sine over k2 v2t. But we already said k2 v2 equals k1 v1. So this equals negative at of sine k1 v1t. So because these has to be the same, so we equate them and the k1 v1t cancels, and all we have left is negative a plus ar equals negative at. And let me double check whether it is the correct expression. And negative at. Yeah, so I think that looks good. And so we can rearrange it so that we have A equals AR plus AT, just as we expected. So that's part A. Let's look at part B. Part B says, assume that the slope of the chord just to the left is the same as the slope just to the right. Show that the amplitude satisfies another relationship. So it asks us to express the amplitude of the reflected wave in terms of the initial wave. So previously what we did is we find the displacement and we match them. Now we're going to do the same thing, except that we are trying to match the derivative. So the derivative to the left equals the derivative of the initial wave plus the derivative of the reflected wave. Of initial wave, what we have is A times K1. Sine becomes cosine. Cosine K1 x minus V1t. But again, x equals 0. So the reflected wave is the same. K1 A reflected, also cosine K1 x plus V1t. Again, x is 0. So this is K1 times A R minus A times cosine. Actually, it is plus because in cosine is an even function, so cosine of negative K1 V1t equals cosine K1 V1t. So K1 V1t. And what about the right hand? We have a transmission and K2 cosine negative K2 V2t, but that is equal to positive K2 V2t inside of cosine. And these two are equal. So let me rearrange my equations a little bit so I have a little bit more space to solve the rest of the problem. Good. So this gives us, again, cosine K1 V1t and cosine K2 V2t can cancel. What we have is K1 over A plus AR equals K2 times AT. And our purpose is to have AR in terms of A. So we first need to cancel AT. And we can do that using what we found in the first half, because AT is A minus AR. Okay, now we can rearrange these two equations to have AR equals K2 K2 minus K1 over A divided by K2 plus K1. So this is the second half of the equation we need to prove. And the next thing is that we want to translate K into V. How do we do that? We have K equals 2 pi over lambda. Actually, it might be, we should probably use this equation instead. We have K1 V1 equals K2 V2. So we can represent all K1 as K2 V2 over V1. And if we plug that in, we have K2 divided by K2. This is numerator become 1 minus V2 over V1. Denominator becomes 1 plus V2 over V1 times A. So K2 cancels, and it becomes V1 minus V2 over V1 plus V2 times A. Okay, and this relationship is what we are trying to prove by matching the slope of the chord to the left and right of the origin. The very last question asks us, what is AT in terms of A? We already know that A equals AR plus AT, and we have AR in terms of A. So in order to find AT, we just have AT equals A minus AR. And A minus AR is 1 minus K2 minus K1 over K2 plus K1 times A. So that is 2K1 over K1 plus K2 times A. Get probably out of space a little bit. And let me again try to put everything a little bit smaller to get more space. So as I said, this is a relatively long question. Okay, good. So that should be enough. So this is how we express AT in terms of A if we use K. And of course, another thing we can do is to use the definition of V, in which case it becomes 1 minus V1 minus V2 over V1 plus V2 times A. And in this case, this can be expressed as 2 times V2 over V1 plus V2 times A. So this is AT in terms of A.